Okay, so this is going to be the lesson for the comparison test is a huge pain, but you have to do understand the basics of it. The idea is simple. Doing it is not is anything but simple. You have two sequences, right? But you have one where the numbers are always smaller. Like, you'd have something like 1/2, and then, this one's one, this one could be 1/3, and then this one is like 2/3, right? This one is always bigger. And the thing is, if the bigger one will converge and add up to something finite, well, then the smaller one has to. That's the whole point of this test is to find something to compare your series to because yours doesn't look like one that you can determine. So this is usually the classic example. They give you our buddy 2 to the n, but then they add a 3 there and from 1 to infinity or from 0, whatever. So you have to, does the +3 really matter? No, but you have to, it doesn't look like the ones we did before. Now, before I show you direct is, this is usually very difficult to do, but I'm going to show you a little secret. So suppose you started with this, because this is kind of what you have to do during these problems, and it's a huge pain in the neck. So, right, 4 is bigger than 2. But if I were to flip these over, flip that one, flip that one, that's a half a dollar. That's a quarter of a dollar, right? This is 25 cents. This is 50 cents. The inequality has to go this way now. So when you start off with the bigger number, right? 4 is bigger than 2, but when you flip them over, the fraction ends up being smaller, right? Because you have the bigger number on the bottom, right? The fraction with the bigger number on the bottom is always smaller. So that was bigger, but now this is smaller. So flip, flip, flip. So when you have something like this, so what I'm going to show you to do here, this one's going to be my AM. I need to compare it to something. So what you're going to compare it to, you're just going to get rid of the 3. You're just going to compare it to 1/2n. Now, this is geometric. The ratio is 1/2. This is going to converge by geometric series. Very obvious. So I'm calling this one Bn. Now, all I have to show is that this one is smaller than this one, and I can use this, right? If the bigger one converges, the bigger one, right? B for bigger, but it's not always going to be bigger. I mean, it's always going to be bigger than the inequality. So if Bn, the bigger one, converges, this one must converge. So I just have to show that this is bigger than that. So I'm going to use exactly what I did here. I'm going to start off like this. This is very clear. This is equal. Now I'm going to add 3 to this side. Now, you took two things that are equal, like 2 and 2, and then you added 3 to this side. Well, there you go, right? I mean, if you're taking something positive and you're adding 3 to it, right? I mean, I started with the same thing, 2n, 2n. I add 3 to the right side, but I don't add it to the other side, right? I'm not doing a balance this time. I'm disrupting the balance. So this has to be bigger. Now I'm going to flip them over like I did here. Let me go back and put that to be a 4. So I'm going to flip, flip, flip. So it becomes 1/2n. That thing flips. That thing flips. So this is bigger. I just showed, boom, that's what I wanted. I need the bigger one to be this because I know that it converges. So this one converges because it's geometric with ratio of 1/2, which is less than 1. So this one converges. So the one that's smaller must also converge by the comparison test, by direct comparison. Now I'm going to do another example to show you this is not always clear cut. Sometimes doing this inequality voodoo works fine if it's something very simple. But if I give you something more complicated, doing this it's impossible to show. I'm going to show you with another example. Okay, so I created another one. Now, first, when you look at it, the +1 and the -2, they do matter. But when you're dealing with infinity, ultimately, the only thing that matters is the highest power on the top and the highest power on the bottom. So this is what allows you to pick the one you want to compare it to. Take the highest power on top, the highest power on bottom. I'm going to do this more in the next lesson when I do the limit comparison, which is a lot easier to do. It's still a pain in the neck. So I want to compare this one. I want my B. Now notice I had to start this at 2. I mean, I'm usually bad here, and I'll put a 1 there. And I mean, it's okay that it can start negative, but you generally want the terms to be positive. So my comparison one is going to be 1 over n. Now, I know this one diverges. Well, let me call it Bn, right? This is my B. Now, this one's going to be a little different. I'm going to want this one. I really should be calling this one B and this one A if I want to fit this, but I'll show you. So this one is going to diverge by the p-test. Now, the thing is, if I had this, if this one is bigger and it diverges, that doesn't mean this has to diverge. This one is smaller. These are smaller numbers that you're adding. This one could very well converge. So what you want in this case is you want this one to be smaller than that one. Because if the smaller one will diverge, then the bigger one has to. So look, if I reverse this and said to you, okay, the smaller numbers add up to infinity, well, then the bigger numbers have to add up to infinity, right? I mean, these numbers are smaller. These are smaller numbers. If you add them up and you get infinity, how the hell are the bigger numbers going to add up to something finite? It makes no sense. If the smaller numbers diverge, the bigger numbers diverge. So in this case, I want to show that this is smaller, right? Whoops, did it wrong. I want to show that this is smaller than that. But this is real. It's doing this with an inequality is difficult to do. I mean, you could start off doing something like this. You could say, okay, this is true. Then if you flip them over, but you see, this doesn't take you anywhere. You need to get an n squared in there. So you can say, okay, this is true, right? If you started with n and you add 1 to it, n plus 1 is bigger than that one. And then, well, then you have to divide them both by n squared. Now that is 1 over n. But then what about the minus 2? Like you can't just create this inequality string. And that's not what I want anyway. So you have to, in this case, what you would do is you'd have to pick a few numbers and plug them into both and show that this time I want this one to be smaller. I need that one to be smaller because I know it diverges. Smaller one diverge means bigger one diverge. So I want to hope that this one's bigger. And really, you cannot do this like I did with the other example, where I can try to actually show this directly. That's the whole point of direct comparison, is to show that one is always bigger or smaller. It is highly impractical. It's very difficult to do with inequalities because a lot of weird things happen. I mean, it's simple in a case like this. I mean, I can tell you that, I know that n plus 1 is bigger than n. And I know that when I flip them, the inequality will switch the other way. But again, that wouldn't be what I want. I want this on the bottom. I don't want n plus 1 on the bottom. So I'm going to plug numbers in. First, I'm going to plug them all into this one. And then I'm going to plug them into that one, right? Let me put 1 over n. I don't know how to do this. All right, so let's see. We're going to put 2 in there. So you're going to get 3. 2 squared is 4. So you're going to get 3 halves. So when I plug into the other one, I guess I'll do it this way. I'll put a little squiggly. And this one's going to be 1 over n. I'm not going to write I'm not going to write this whole thing over again. So I'm going to plug 3 into there. That's going to give me 4. 3 squared is 9. 9 minus 2 is 7. Now I'm going to plug 4 in there. 4 plus 1 is 5. 16, right? 4 squared is 16 minus 2. Okay, now I have no idea what these are. This is why I have this. And now plugging them into 1 over n is easy. This is 1/2. Clearly, 1/2 is smaller than 3. I mean, look, they have the same bottom. Here you get 1 over 3. And here you get 1 over 4. Okay? Now, it is obvious to me looking at them, right? I know that's 0.333. So 4 divided by 7. I want to be precise here. So this one is 0.571. So again, smaller, smaller, smaller. Now, 1/4 is 0.25. 5 over 14. I know it's, whoops, 5 divided by 14. I did 15. That is 0.357. Again, bigger, 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 bigger. Now you could start going crazy and plug something in like 10, but usually if you do a few, yeah, the danger with this, there are some where for the first 5 or 6 numbers, one of them is bigger. And then all of a sudden when you start plugging in 6, 7, 8, it switches and then the other one is smaller. So it's like you have to be careful with these. But as a general rule, if it looks like these numbers are always bigger, now they're going to get close together. The whole point of this is this his behavior matches up to his behavior. That's the whole point of doing comparison. This dude will end up doing what he does, and his numbers will end up close to his numbers. So these numbers at the end might get really, really close together. Like you might have point 0.1, and this one might be 0.11, or even to go even one better. It might be like 0.09, which is still bigger. Actually, no, it's not. It has to be like 0.11, something like that. So like, but the numbers will get really close together. Like that's the whole point. But these will always be slightly bigger than those. So since this one is smaller and it diverges, then it forces the bigger one to diverge. So again, it's confusing, it's complicated, and it's annoying, and it's difficult to do. It's almost impossible to do the inequalities on these. That's why if I gave you one to do by direct, it would be really, really simple one where you could literally just plug the numbers in and show that they're smaller or bigger, depending on what you need, right? If you're looking for converge, you need it to be bigger because you want the bigger one to converge to force the smaller one to converge. If this one adds up to a finite thing, then this one must. Or if you want this one to diverge so that that one diverges, right? So it depends what you need to do, but you can always plug a couple numbers in, or you can try to do the inequality thing, which is again impractical, complicated, confusing to do. So the limit, that's the direct comparison. Limit test is a little less confusing, but the point of these is always the same. Find something to compare it to. And what you compared it to will end up doing the same thing yours does. The hard part is this. Showing that is really difficult to do in general. So usually this test is not very useful, but it's done. So I'm going to do the limit comparison test after this. Okay.